Okay, we're going to continue on here. Chapter 17, electrochemistry. So as we talked about last time, we're just going to up front here kind of do a little review of all the redox stuff to make sure everybody's on the same page. So last time we talked about oxidation reactions, which once again are typically things that will lose electrons. Things that get reduced will gain electrons. Remember, you could kind of follow the oxidation state or number. And again, if you kind of just take a basic number line, if the change in the oxidation state from reactants to products is moving in the positive direction, then that thing is going through oxidation. If you look at the change in oxidation state from reactants to products and it's moving in this kind of negative direction, it is going through reduction. And remember that there's also the oxidizing agent, which again is the substance that gets reduced, while the reducing agent is the substance that gets oxidized in this case. And again, the reason they're called the sort of reducing agents, oxidizing agents, is they do cause the opposite effect in the other substance. So if somebody gets reduced, it has to gain electrons. In order for it to gain electrons, somebody has to lose electrons. So it is causing the oxidation of something else, and vice versa there. If somebody gets oxidized, it will lose electrons. By that process, somebody will have to gain those electrons and get reduced. So the agents, again, as we talked about, is a different question than what is being oxidized and what is being reduced versus the oxidizing agent and the reducing agent. We talked about how to assign oxidation states, and remember, for the most part, you want to kind of start with oxygen. It usually is -2, except obviously if it is peroxide, then it's -1. Again, if you have some type of, like we looked in an example there, a 3-pack of sort of elements, usually again you want to kind of start on the right there with the oxygen. That gives you a -6. Go to the left, +1 for hydrogen. And remember that the oxidation states do need to add up to the overall charge. So once again, that's -1. And in this particular case, that means that the carbon here will have a +4 oxidation state. And when you do assign oxidation states or give oxidation states, again, you do need to give the charge. So it is +1 for hydrogen. Oxygen is -2. It is not the grand total of everybody. It's just individually -2. And carbon here would be a +4 situation in this case. So assigning oxidation states are really important in sort of electrochemistry because again, it allows you to understand sort of what's happening, what's being oxidized, what's being reduced. And later on, when we talk about galvanic cells, that's really important to understand sort of what will be your like anode and cathode when you kind of put a galvanic cell together. Any questions on that stuff there? All right, so, and we talked about basic sort of half reactions. And again, if you have a basic sort of half reaction, this would be a oxidation half reaction. And again, it's an oxidation half reaction because the electrons there are on the right-hand side. If you had something like this would be a reduction half reaction. Again, you have your electrons on the reactant side like they're being gained. This can be a reaction where you add it together. They're called, again, half reactions because when you put them together, you get the overall reaction. One of the important things before you can add these reactions together, again, you do need to make sure that there are the same number of electrons in each half reaction. And obviously, we only have 1 here, and we obviously have 2 here. So we do need to multiply the first half reaction by 2 all the way across. That way, when you add these reactions together, electrons should always completely cancel out. They shouldn't be left. And you'll be left with really a balanced redox reaction here. Plus some chlorine goes to 2 sodium chlorides in this particular case. And again, what's basically happening here is electrons are heading over from the sodium to the chlorine in this particular case. Again, the sodium here being oxidized, releasing those electrons, and the chlorine here picking them up and being reduced. Any questions on that there? All right, so in basic sort of half reactions, that's pretty much all you kind of have to make sure of is like the electrons are equal on each side. But when we are dealing with sort of redox reactions or balancing redox reactions in either acidic or basic conditions, there's a few extra steps that we have to do to sort of balance these type of reactions. So just to kind of go through this again to make sure you remember it or you understand what you're supposed to do. So if we have this particular reaction here and we wanted to balance it in acidic conditions, the first step that we want to really do is split off our half reactions. So the easy way to do that is just take the elements that are the same on opposite sides of the arrow and put them together. So there's an iron there, there's an iron there, and there's a chromium over here, and there is a chromium over here. Also, probably a good idea to kind of think about oxidation states and numbers so you can understand sort of what's going on. So in terms of oxidation states, iron with a +2 charge has a +2 oxidation state. We actually did this one at the very end last time. That's -2, which gives us a -14. We saw that each of the chromiums are +6 in this case. The iron on the other side would be +3. And lastly, the chromium here would be +3. So again, if you want to kind of use the little number line to figure out what's going on, you could look at the iron, which starts at +2 and ends at +3. It's becoming more positive. So the iron here is going through oxidation. By default, the dichromate here is going through reduction. And that would mean that this is our oxidation half reaction. This is our reduction half reaction. That would also mean, by the way, that the iron 2 here is our reducing agent. And the dichromate here, which is getting reduced, is our oxidizing agent in this particular case. All right, so it's a good idea to sort of get that worked out usually before you kind of jump into the balancing so you understand if you're kind of doing it correctly as you go through it. So the next thing that we want to do when we balance these type of reactions is we want to balance every other element except for oxygen and hydrogen. And we're just going to balance it like a normal equation. We're going to use coefficients and just balance it. So obviously in the top oxidation half reaction, we have one iron on each side. So that's all good. In the bottom, we have two chromiums on the left, but only one on the right. So again, just to balance it like a normal equation here, we're just going to put a 2 coefficient. Once you've pretty much balanced all the other elements except for oxygen and hydrogen, then it's time to balance the oxygens. And the method that we use here is sort of the water method. We balance the oxygens by using water. So basically, whatever side needs some oxygen, we put an appropriate number of waters on that particular side. Now, the problem with doing that is obviously you're not just adding oxygen when you add water, you're also adding hydrogen. So we go to one side with the waters, and then the opposite side, we add 2 H pluses for every water we add. So one side gets the water that needs the oxygen. The other side gets a couple of H pluses for every hydrogen or water that we added. That way, at the end, you will not be short some hydrogens. By the way, if you are at some point kind of short hydrogens to begin with, you could also add an H plus to the opposite side just up front and balance out the hydrogens before you begin as well. So in this particular case, if we take a gander here, there's obviously no oxygens in the top reaction, so we don't have to worry about it. In our chromium reaction, we have 7 oxygens on the left, none on the right, which means we do need 7 waters basically to be added there on the right-hand side. Because we added 7 waters to the right-hand side, again, so we don't end up with too many hydrogens, or not enough hydrogens, we will have to add 14 H pluses to the other side. Any questions on that there? At this point, you should hopefully be balanced in terms of elements. You should have the same number of elements on each side of the half reactions. Now what we're going to do is balance out the charge, the overall charge on each side of the arrow. We're going to use electrons to do that. So they're negatively charged. So we need to put the electrons on whichever side is going to help us balance out the charge. The charge on each side of the arrow does not need to be 0. They just need to equal the same number on each side. So obviously looking at the top one, the overall charge here is +2. Overall charge on this side is +3. That means we do need to add an electron to the right-hand side. That will give us a +3 and a -1, gives us a grand total of +2 on the right to match the +2 that we got on the left in this case. If we look at the bottom, we could just take overall charge here. So that's like a +14. This entire thing, I don't care individually, that's a -2. And that is a +12 overall. Again, you shouldn't do more work than you need to. Remember that all the oxidation numbers for each element needs to add up to the overall charge. So you don't really care individually. That whole thing ends up at a -2 when you're all said and done. On the right-hand side, that's a +6, and that's a 0. In this particular case, we will need, it looks like 6 electrons over here on the left-hand side. That's going to give us a -6 and a +12, gives us a +6 on the left, again, to match the +6 here on the right. Any questions on that there? Now, like I said before, figuring out what is the oxidation and what is the reduction half reaction at this point is really a good idea. And that is because we do know that in the oxidation half reaction, our electrons should end up on the right-hand side, which they did. In our reduction half reactions, they should end up on the left-hand side, which they did as well. They should never end up on the same side because then you screwed up. Yes, so they should always have to cancel out. So they should always end up on opposite sides. So at this point, we're really ready to just add these reactions back together. I'm going to erase some of this little addition stuff here just to get some room. And remember, though, like normal, before we add together any half reactions, the one thing that does need to be the same in each is the number of electrons. And in this particular case, we could hopefully see we have 1 electron in the top one and only 6 in the bottom. So we do need to multiply the top equation by 6. And again, we're going to multiply everybody up there by 6. So a 6, 6, and 1 more there. And at that point, we now should hopefully have the same number of electrons, and we can now add these together. That should allow our electrons to completely cancel out. At this point, you could also look for other things that may cancel out or reduce itself down. And in this particular case, there is nothing else. So we have everything on the left-hand side stays there. So 14 hydrogens plus a Cr2O7, 2 minus, plus 6 of the irons. Go to 6 iron 3s on the other side, a couple of chromiums, and 7 waters. Now, if I did not screw up anything here, there's a 50-50 shot. We'll hope. We should be balanced basically in 2 ways. We should be balanced like a normal equation, which means we have the same number of elements on each side. So on the left-hand side here, we have 14 hydrogens. Right-hand side, 7 times 2 is 14, so that's good. Chromium, we got 2 on the left and 2 on the right, so that's good. Oxygen on the left, we got, looks like 7. And on the right there, we got 7. And iron on the left, we got 6. And on the right, we also have 6. So it is balanced in terms of a regular equation. We also should be balanced in terms of charge. So the overall charge on the left-hand side of the arrow and the right-hand side of the arrow should equal each other as well. So that's going to give us a plus 14 for the hydrogens, a minus 2 for the dichromate, and a plus 12 there for our iron. Adding all that together, that's 14 and 12 is plus 26 less 2 gives us a grand total of plus 24 happening there on the left-hand side. Right-hand side, we got a plus 18 for the iron, a plus 6 for our chromium, and a 0 for our water. And 18 and 6, I hope, is plus 24. So again, we're balanced in both ways, like a normal equation. Same number of elements, and the overall charge on each side is also balanced. First off, any questions in that? This would be balanced in acidic conditions. Now, if you wanted to balance this reaction in basic conditions, you basically would just do the exact same thing. It's probably the easiest move. Just balance it in acidic conditions first. And at the end, you could just then turn it into a basic equation at the very end of it. It's probably the easiest way to do that. So if we were going to do that, I'll steal there's some room up here to do it. So if we wanted to do basic conditions, we're just going to basically do exactly what we did there a second ago. And we will end up with obviously the same equation we just did, which was 14 H pluses plus Cr2O72 minus plus 6 of the iron 2, go to 6 of the iron 3 plus 2 of the chromium and 7 waters. Now, if we wanted to do, like I said, basic conditions, what we actually do in basic conditions is we actually add OH minus to both sides. So what we do is we add OH minus to both sides. The amount of OH minus that we add to both sides is equal to the amount of H plus that we have. So in this particular case, we have 14 H pluses. So that is the amount of hydroxide we add, again, not to just one side, but both sides. Now, the side where we added the 14 hydroxides and the H plus that's also there, these guys will combine to make 14 waters. And when they combine to make 14 waters, that means you usually have a chance to reduce down the water. So we got 7 on that side, minus 14 is going to net leave us 7 waters on the left, plus everything else that's there. And again, at this point, we should still be balanced in both ways. So once again, we have 14 hydrogens on the left. We got 14 on the right. We have 7 and 7 is 14 oxygens on the left and 14 on the right. We have 2 chromiums on the left and 2 on the right. We have 6 irons on the left and 6 irons on the right. Overall charge, 0, minus 2, plus 12. That is a plus 10 overall on the left. That's a plus 18, a plus 6, and a minus 14 for the hydroxide. That's a lot of math there, but I think that leaves me a net of plus 4 and plus 6 gives me a plus 10. And we got the same overall charge on each side of the arrow. Any questions on that? How do I know if I'm just looking at this that I balanced it in acidic conditions versus basic conditions? Well, in the acidic conditions, there's H plus, and in the basic conditions, you end up with OH minus in your equation. So again, that's how you could tell it's acidic or basic is you should end up with either H plus or OH minus in your equation. Any questions on balancing that there? All right. I tried one. You try one. Fun. Why don't you do this one here? We'll do I minus. Maybe not with that. Go I minus plus a little MnO4, a little I2 and MnO2. Let's do basic here. Whoops. Okay, so let's see how you're doing. So once again here, we're just going to split it off into our half reactions. Just go like elements together. And then I got some MNs over here. Bless you. We could also sort of figure out which one's which. So if we take a look here, our iodine has a -1 oxidation state. That is -2 for the oxygen. That's going to give us a -8 overall. We do need to end up with a -1. So that means that the Mn in this case is +7. The I2 is naturally how it comes. So that's a 0 oxidation state. The oxygen here at the end is -2, and that's going to give us -4. No charge overall. That's going to be a +4. That is happening there. That we just kind of take a peek here at what's going on for our iodine. We're starting at -1, which would be here, and we're ending at 0. And that means it's becoming more positive. So this is going through oxidation. This is going through reduction, as it is going from +7 to +4, moving in the negative direction in this case. That would mean that the iodide here is our reducing agent, and the permanganate is our oxidizing agent in this case here. Any questions on that there? All right, so off the balancing here, we do need a 2 for our iodine, and that we can then move on to oxygen, and we're going to use water to balance that. No oxygen in the first one. Second one got 4 oxygens on the left and 2 on the right. That means on the right-hand side, we need 2 waters. And because we put 2 waters there, we will need 4 H pluses on the other side. Now we are ready to balance out our charge. So that's a -2 overall, and that's a 0. That means we need a couple of electrons there in the first one to give us a -2 on each side. And that's balanced. Bottom one, that's +4. That's -1. That's a grand total of +3. Over here, we got 0 and 0. So that means we need 3 electrons over here, which will give us a -3 and a +3, gives us 0 to balance it out in that case. We once again have added the electrons to the correct side based on our oxidation and reduction. Our oxidation gets the electrons on the product side, and our reduction gets it on the reactant side, which is the correct way. At this point, we're ready to add these together, but once again, we make sure we have a number of electrons in each half reaction, and obviously we do not. So common number between 2 and 3 is 6. So we do have to multiply the whole entire top guy by 3, and this whole entire bottom one by 2 to give us the same. That's going to yield us up on top there 6 I minuses, 3 I2s, and 6 electrons. On the bottom, we're going to end up with 6 electrons plus 8 H pluses plus 2 MnO4 minuses and 2 MnO2s and 4 waters at this point. We are now good to add these together. Electrons should completely cancel out, and in this case, I think that is it. That will leave us 8 H pluses plus 2 MnO4 minus plus 6 I minus. So everything on the left-hand side of the arrows stay there. Everybody on the right-hand side of the arrows stay there as well. So 3 I2s plus 2 MnO2s and 4 waters. There we go. And once again, we should be balanced here in acidic conditions, as we can see the H plus there. 8 hydrogens on each side, 2 Mns. We got 8 oxygens on the left. We have 4 and 4 on the right, which is 8. 6 iodines on the left, 6 on the right. And overall charge on the left is a 0. That's plus 8 for the hydrogens, minus 2 for the MnO4, and a minus 6 there for the I minus. So that's going to give us 0 and 0. So we definitely balance them both ways. Now we can simply turn this into basic by adding hydroxide to both sides. Remember, the amount of hydroxide is always equal to the amount of H pluses. 8. So we are going to add 8 OH minuses to the left, and we'll add 8 OH minuses to the right. That is going to give us 8 waters over here on the left. And then we could reduce down our waters to 4 waters, plus a couple of these guys here. And we get that, and our 8 OH minuses. And at this point, we should now again be balanced in basic conditions. We should still be balanced both ways. So once again, 8 hydrogens on both sides. We got 8 and 4 is 12 oxygens on both sides. Hopefully more than that, I think. Where are we at there? And we should hopefully, we got 4 and 8 is 12. That is 4 and 8 is 12. There we go. I can count. All right, good. 2 MNs on both sides and 6 iodides on both sides. Overall charge on the left there is -8 and -8 on the right there. So we should be good in that particular case there. Yeah. Any questions on balancing these equations here? All right, so hopefully that was a little review for you, since you should have hopefully done it there in 200A. So we're then going to kind of go off to really the main part of the chapter, I think. And if you want to practice some more, there's a few extra problems in here if you want to kind of do them. Balance them. All right, so we're really going to talk now about sort of the main part of this chapter, which is electrochemistry and galvanic cells. And this is an example of a galvanic cell that you could build in the laboratory. And a galvanic cell typically has a few parts to it. It has one part which is known as the anode. And on the anode side of the compartment, that is where oxidation occurs. And basically, when oxidation occurs, those electrons go out through a wire, through a voltage meter, and off to the other side, where we call that the cathode side. And the cathode side is where reduction occurs. So a galvanic cell is essentially a redox reaction, where we kind of have two sides separated out. We have typically, when we make a galvanic cell, we typically have a solid electrode on each side. And whatever that sort of solid electrode is, we will also have an aqueous solution that contains those ions. So over here, we got some copper on one side, we got some zinc ions floating around in the solution. We also have a salt bridge that spans both of the compartments. A salt bridge is usually filled, much like the name implies, with some type of salt solution, like in this case, potassium chloride. And what happens is, as the cell is running, the ions will drop this way, the positive ions, and the negative ions will actually go this way. There is a potential difference between the cathode and the anode. The anode you can think of as being kind of like more positive, which helps bring the electrons, which are negatively charged, away from the anode side to the positive sort of cathode side and bring it over there. Now, what happens is basically on the anode side here, we have the solid zinc in our electrode. When it loses its electrons, that solid guide jumps out into solution and becomes a positive zinc ion in this case, as it has lost electrons. When those electrons again travel to the other side, they come on down and they pick up with some floating copper ions, and these guys on this side get out of the pool and basically become a solid. So on this side here, they jump in the water. On this side, they get out of the water there, basically, as they gain. Now, what is really the function of the salt bridge? The function of the salt bridge is to keep everything flowing correctly and not to build up the wrong type of charge on one side of the cell that you do not want. So, for example, if I were to run this cell and take out my salt bridge, a cell such as this, we would again have a compartment here with our zinc and our zinc guys floating around, along with our other ion, or sulfate ion in this case. And on the other side there, voltage, we would have our copper in our beaker with our copper guys floating around, and sulfate as well in that case, right? So the idea here is if I kind of pull the salt bridge from it, what's going to happen is these electrons will travel to the other side, right? And again, as they travel to the other side, and as this guy loses electrons, what's going to happen on our left-hand side here of our compartment is we're going to get into that solution a lot of zinc ions, which are positively charged. So the zinc ions are going to start dropping in there, and we're going to build up a lot of positive charge over there on the left-hand side. What's going to happen on the right-hand side is all those positive copper guys are going to come out of solution as they will gain those electrons. And that's going to leave pretty much in the solution the negative spectator ion, which means you're going to start to build up in the solution a bunch of negative charges over there. And that's pretty problematic since we have negative electrons trying to head in that direction because, as we know, things with the same charge do not like each other. Yes. So they are repelled by each other. Things with opposite charges like each other, which means as you build up this big old positive charge on this side, your electrons are going to go, why am I leaving? I'm just going to stay over here because I like the positive charge over here. So you're going to want to go across to the other side, and your cell will obviously not function very well at that point. So that is with the purpose of the salt bridge. You insert your salt bridge here. So as you're building up this positive charge when those ions go into solution on this side, they are countered by the negatively charged ion that's in the salt bridge. So those negatively charges go in there, and you don't get that big buildup of positive charge on that side where you don't want it. And same thing over here, as you're getting that buildup of negative charges, the positive ion in the salt bridge will head over there to that side and again sort of counteract that big buildup of negative charge. And that's going to allow those electrons to flow really well from one side to the next, because you really do want a little bit more positive on that side to help kind of pull the electrons to the other side. And again, without that salt bridge there, you're just going to get up the buildup of wrong charge in each of those compartments, and that's not going to allow the electrons really to flow from one side to the next, because again, you're just going to kind of stick them there on the left-hand side. They're not going to want to leave. Any questions on what the purpose there of the salt bridge is for? Okay. So ultimately, this is, once again, like I said, just a redox reaction. We can see on the cathode, I'm sorry, the anode side, we basically have our solid zinc going to our zinc with a +2 charge and giving off those 2 electrons. On the cathode side, we have our copper picking up those 2 electrons and basically coming out of solution as solid copper over there. By the way, that gives us our overall reaction. If we add it together, electrons cancel, then we get that overall reaction that we see on the bottom there, which is the zinc plus the copper 2 ions floating around goes to our zinc with a +2 and our solid copper over here. So basically what's happening is this guy is sending electrons over to the copper 2 Copper 2 is accepting it. And obviously, again, the copper 2 here is being reduced and the zinc is being oxidized in this case. Any questions on that there? All right, so those are the major sort of components, obviously, of a galvanic cell. Those electrons can go out and do some type of work, like positive voltage is good, right? Kind of like in a battery, get positive voltage there, things operate. Now, in a galvanic cell, the difference between the electrical potential between the anode and the cathode is sometimes referred to as the cell voltage. A volt is 1 joule of work per coulomb of electrical charge that is transferred. So 1 volt is equal to 1 joule over a coulomb. It is also sometimes referred to as electromotive force, EMF, or cell potential. Essentially, in chemistry here, if they ask you for any of those things, they're basically asking you to calculate the cell voltage in a problem if you're asked to calculate any of those things. As I mentioned before, again, there's sort of a charge difference, if you will, that helps bring those electrons and pull those electrons from the other side. Again, if we kind of zoom in there, you can kind of see the salt bridge right there between the two. And again, we got some nice positive voltage happening here, which is pretty good in this particular cell. So here is our overall reaction in that particular example. We could also write this equation sort of a shorthand or show the galvanic cell in a shorthand demonstration or way, and that is what is known as a cell diagram. And when you write a cell diagram, it is always anode on the first part, you cathode. So that is always the order at which you write a cell diagram. And you basically have both parts here. So in our anode compartment, we have our zinc and our zinc ions that are floating around. The two lines here represent the salt bridge. So that's the salt bridge representation. And over here we have our anode compartment, our copper going to our solid copper. As you can see in this particular one, sometimes they will include the molarity, and sometimes they definitely will include it if it is not 1 molar, which is standard concentration. And sometimes you will also have other things in these cell diagrams. Sometimes you will have pressures. There are certain anodes and cathodes that are gases, and sometimes they will use something as a physical electrode that is not that, like graphite, platinum, or something like that, as a physical sort of electrode, because obviously a gas wouldn't be in a solid state, and they're using that. Now, how does the organization really go? Well, pretty much it goes like this. First guy is your reactant. Second guy is your product and the overall reaction. Next one is your reactant. Next one's your product. So that is how you can kind of turn it into an equation from the cell diagram. Is kind of reactant, product. And then you could kind of turn that into your, again, overall reaction. So first guy there, again, is our reactant. So that would be our zinc. Next guy is our product. So that would be our zinc with a +2 charge. By the way, just a reminder, right? Those are not the same thing, right? One is solid and one's an ion floating around in a solution. So they are not the same thing. They are both zinc, but they are different versions of zinc. Going to the other side, we have our copper 2 and our solid copper on our product side. So again, you can recreate the equation from the cell diagram, basically following that reactant, product. Now, when we deal with galvanic cells, there's something that we oftentimes will sort of look at, and that is standard reduction potentials. And standard reduction potentials are sometimes abbreviated as an SRP for short, standard reduction potentials. So if we built this diagram here, or this cell, in this particular case here, our zinc is going to be our anode. Our hydrogen in this case is going to be our cathode. And once again, this is an example, as I mentioned a second ago, that you may see some other things in there. So here we are using platinum as the physical electrode for hydrogen, since it's a gas. and that puts in there. And since hydrogen is a gas, we see that it's at 1 atmosphere, standard um, pressure. And we can see that our solutions are also at 1 molar, which is a standard concentrations. So in this case, our zinc is going to give up our electrons. So our zinc half reaction, as you can see there, zinc going from 0 to +2, becoming more positive, losing electrons. It is the hydrogen here going from +1 to 0 in this case that is getting as it picks up those electrons. Again, you could get the overall reaction, reactant, product, reactant, product. This is not usually included in the equation because, again, it's just there for the thing. And what's blocked out on the bottom looks something like this. The zinc on one side, ours zinc 2 plus on the other side. And then we have our hydrogen on this side. And we have our H2 on that side in that particular case. And this is the overall reaction that is taking place. Obviously here we need to balance it out. So we do need 2 of these guys. And here we're going to have electrons being transferred from the zinc to our hydrogen. And again, reducing our hydrogen down to H2 in this particular case. So when we do this, we can get a obviously cell voltage when we hook these 2 guys up. And when we talk about SRP values, standard reduction potential values, or SRP values, much like most things in chemistry, when they can't directly maybe measure things, oftentimes we'll choose something as a standard to compare everybody to. Bless you. In the case of SRP values, they chose the hydrogen electrode as the standard to compare everybody to. This is sometimes referred to as the SHE for standard hydrogen electrode, and they arbitrarily sort of assigned it a value of 0 volts. They are called a standard reduction potential because when you look at these reactions, they're all written as reduction reactions. So you can see here, electrons on the reactant side, these are all written as reduction reactions. And for hydrogen, which is our standard hydrogen electrode, it has a value of 0. So what they basically could do now is just kind of hook everybody up with hydrogen, measure the voltage, and then they can figure out the SRP values for basically everybody else by doing so. And so, for example, here, if they hooked up hydrogen with zinc and they sort of ran it there, they will end up with a cell voltage of 0.76 volts. And what that means is they could use this equation to figure out what is the SRP value for zinc. In this case, once again, our zinc is our anode, and our cathode, again, is the hydrogen electrode. This is the formula that is used to calculate the cell voltage in a galvanic cell. Now, when we use this equation, and it may not make sense what I'm going to say right now, we actually, when we go to a table, we do not change any signs that we find in the table because that is why we are subtracting here. So there is an SRP table we'll teach very shortly where you'll look up at the value, for example, for hydrogen, for zinc, whatever else you're looking up. And when you find those reactions and those values in the table, like you see here, zinc is minus 0.76 volts. You actually keep the values for everybody the exact same when you use this equation because the subtraction is basically helping you figure that out and changing the sign for you. The reason you need to change the sign is this. In this particular case, we have zinc. If we went to the table, you would find something like this, which is zinc plus a couple of electrons will give us solid zinc, and it would have an SRP value of negative 0.76 volts. You would also, obviously, when you go to the table there, you would find a little hydrogen there. and it would gain an electron. And in this particular case, you would put the 2 to balance it all out, so it's all nice. And we'll end up with H2. And this would have a value of 0 volts. Now, when we have a galvanic cell, because it's a redox reaction, we have the anode where oxidation takes place, and we have the cathode where reduction takes place. Now, for the cathode in this situation, you are good when you go to that table because every one of those reactions that you'll see in that table are written as reduction reactions. So they are perfectly fine. They are not written as oxidation reactions, which means, technically speaking, if my zinc is my oxidation reaction, which it is in this case, this reaction right here, how it's written in that table, is actually incorrect. It is not a oxidation reaction, it is a reduction reaction. To make it into an oxidation reaction, we actually would have to reverse the reaction around, and we would actually have to have zinc going to zinc with a +2 charge and 2 electrons. And that would be the oxidation reaction that is happening. Now, when you reverse one of these reactions, what happens to the SRP value that you find in the table is the sign changes. So instead of it being minus 0.76 for the oxidation reaction, this would actually be positive 0.76 volts, sometimes referred to as the standard oxidation potential rather than standard reduction potential. Now, the reason we do not change, for example, the sign is this equation with the minus will change the sign for you. So if I wanted to calculate E of this cell, I would go E of the cell is my cathode, which is zinc, minus, my cathode is hydrogen, which is 0, minus my zinc, which is my anode, and that's going to be minus 0.76 volts. Minus and a minus gives me 0.76 volts, which is the cell potential that we have when we measure it. So even though technically speaking, the anode one should be reversed, if you use this equation with the minus and the subtraction, you should not change the anode one because it will do it for you. So you don't have to think about it. It will actually just change the sign for you without remembering it. Now, if you want to be sort of correct, if you will, and reverse your reaction like we did here, you actually should add the values after you change the sign. So if you decide you want to change the sign for the anode, you should actually just add those values together. So if you want to actually change the sign, and it will always be for the anode reaction, you would then want to go E of the cell is equal to E of the cathode plus E of the anode, because you have already changed the sign. And if you did that on this one, it would get you 0 volts plus 0.76 volts, gives you 0.76 volts. So the easy way to think about it is maybe just choose one way and stick with it. Yeah. And people will teach you both ways in books sometimes, like add them together because you should change the sign, or if you don't want to change the sign, subtract them. So if you subtract, don't change the sign from the table. If you add them, you need to change the sign from the table. Don't do both, otherwise you get the wrong answer, obviously. Any questions sort of on that there? So again, what we see here is we could hook this standard hydrogen electrode up with anything. We could measure the cell voltage. Again, using this equation, we could figure out the SRP value that we would find in the table. And that's basically what they did for everything. Here, if they did it, here is a table from your book, or a similar table from your book here. And again, you can see when you look at these are all written as reduction reactions. So you can see they all have the electrons on the reactant side. These are all reduction reactions, which means, again, technically speaking, one of these equations in here should get reversed because again, it's a oxidation reaction that's occurring. Maybe doesn't want to move. It's frozen. All right, let's just look at this table here. That's a little better, I guess. All right, so again, same idea. You could look here and you can see everybody is written in the reduction. So once again, if you had to do it, you would have to change it. So if you take it from this table or an SRP table, don't change the sign if you subtract. Once again, change the sign if you do. So if we take a look here at some of the other important things about these values that you find in this table. One thing is when you write that E value there, it is specific for how the reaction is written. So if it is the reduction reaction, you should have it. Technically speaking, if you reverse that reaction like I did with the zinc and write it as an oxidation reaction, you should change the sign because the value you see for E should be specific for how the reaction is written. Now, how do you know if you're just told, hey, you're going to build a galvanic cell out of these two things? How do you know what should be, say, your anode and what should be your cathode? So you can use these SRP values to help you decide. And pretty much the only thing told to you is you just built a galvanic cell out of these two things. The more positive SRP value that you find, the greater the tendency for the thing to be reduced. Now, when we think about anode and cathode, this part of the galvanic cell that gets reduced is the cathode. So in general, if you're putting two things together and you want to build a galvanic cell, you would want your more positive SRP value to be your cathode. And obviously by default, your more negative one to be your anode in this case. That is what you should follow when you're trying to decide what's your anode and your cathode. Only if you are not given any information about what is going on in that reaction. So the thing that people always screw up on is they're given an actual equation in the problem that shows you what's happening, and they just go to the table and go, cool, this one's more positive, that's going to be my cathode, and not even looking at the equation. So if you are given an equation, you actually have to look at the equation and see what is being oxidized and what is being reduced, and that will tell you what is going to be your anode and your cathode. Or if you're told in Word how the reaction is taking place, you need to figure out what's being oxidized, what's being reduced to determine your anode and cathode. But if you're not given any information other than, hey, you just built a galvanic cell of these two things, you can use the SRP value to determine which one should be your cathode, and that should be the more positive one. As we just saw with the zinc one that I did, these reactions are reversible. When you do reverse the reaction, what happens to the SRP value is the sign changes. So if it was positive and you reverse it, it'll become negative. The value will be the same value, just the sign changes. And vice versa, if it was positive and you reverse it, it'll become negative. Now, one of the things that is also important, and as we saw, sometimes you will have to multiply half reactions by a common number to get the electrons to cancel out. Unlike things like delta H and stuff like that, if you multiply these reactions by a number to get your electrons to cancel out, you do not multiply the SRP value by that number. So the SRP value is unaffected by if you need to kind of multiply by a common number to get the same number of electrons. So that's the important thing as well. All right, so why don't we try one here? What is the standard EMF of this cell made of cadmium with 1 molar cadmium nitrate and chromium electrode with 1 molar chromium nitrate, chromium 3 nitrate? Why don't you also write the balanced equation for this one as well? And obviously ID or anode and cathode. Yeah. So off in this case, we're not really told how the cell is hooked up. So in this case, we are free to use the SRP values. And again, if they were not given to you, you would have to go to a table there to get those. And most likely that's what you have to do. We're going to take the one that is more positive, and that should be our cathode, which means this one, even though they're both negative, that looks a little bit more positive. And then by default, this would be our anode in this case. Now, I could calculate the voltage of the cell here by doing, again, my cathode minus my anode. Once again here, I'm going to take the minus version of this, which means I'm not going to worry about changing any values that I find in the table. I'm just going to pop that in there, and we're going to go negative 0.4 volts minus a minus 0.74 volts. Once again, that minus right there is going to change the sign for me to do that. And that's going to get me a 0.34 volts for this particular cell, which is not too bad since it's positive. First off, question on that calculation. Now we also want the balanced overall equation. So technically speaking, this guy right here is perfectly good the way it is written, since it is a cathode, and that is a reduction reaction. Since this guy is my anode, technically speaking, this reaction needs to be reversed. So we got cadmium the way it is. It's all good. And we got E naught is equal to minus 0.4 volts. We should reverse our anode in this case, which would give us chromium goes to chromium 3 plus 3 electrons. And again, when I reverse that, that will now make that positive 0.74 volts. By the way, I cannot add this together at this point because we have different numbers of electrons, right? So really, I got to take this top guy here and multiply it by 3. Take the bottom guy here and multiply it by 2 so that we end up with the correct number of electrons, which is 6 in this case. So I'm just going to read you that right now. So multiplying, come back here, multiplying the top one there by 3 will give me a 3 there, will give me a 6 there, and will give me a 3 here. Remember, multiplying that by 3 will not have any effect on the SRP value in this case. Multiplying the bottom guy by 2, 2, 2, and 6 in this case. Once again, will not have any effect on that right there. Now, if I add this together, my electrons are going to properly cancel out, and I will end up with 3 cadmiums plus 2 chromiums go to 2 chromiums plus 3 cadmiums in this case. Aqueous and solid. By the way, that should be perfectly balanced. There's 3 cadmiums on each side, 2 cadmiums on opposite sides. Overall charge on the left is +6. Overall charge on the right is also +6. Now, the alternative to doing the subtraction for E of the cell is if you want to do what we just did here, which is you yourself change the sign on the anode. If you want E of the cell at this point, you should again just add these values together after you've changed the sign, and you will end up with the same voltage. So again, if you change the sign, add them. If you don't change the sign, subtract them, yeah? And again, I would pick one way of doing that so you're not bouncing back and forth.